Hello and welcome to the tutorial number 5. Today we continue the theoretical discussion about stochastic optimization, and will continue the discussion from tutorial 3. On the tutorial 3 we considered two-stage optimization model, and that model is like focused on the objective function. According to that model, we optimize the expected profit or expectation of the objective function. Today we look at the chance constraint approach, according to which we so we formulate one-stage model, not the two-stage model, but in this model we allow some of the constraints which are related to the scenarios to be violated. So we say, all right, we have three scenarios. We allow ourselves not care about some non probably about the scenarios which have not that high probability, like one of the scenarios, and we don't care about this that scenarios. You can check the details in the lecture. I will not repeat the whole lecture. This is the chance constraint, and example is we are using the Dakota model to continue the discussion. And then in exercise 2, it will be short presentation of robust optimization, just to give you a conceptual understanding what that is as another approach in the domain of stochastic optimization. And we start with first approach of chance constraint. It's optimization, it's fat solution. So I will shortly go to the lecture, and there is an explanation what fat solution is. So according to the fat solution, we want to construct such a model that whatever scenario realizes in the future, none of the constraints from none of the scenarios are violated. Let's look now at the Dakota model. So it's the model, the deterministic model from the third tutorial. I will not repeat it again. You can check it back. What's most important for us here are these demand constraints. We just say that the production of the product, they should be less or equal to the demand. And because we cannot sell more than the demand. And why? It's the produced and manufactured, so sold and manufactured quantities of the product. And in this stochastic explanation or version of the problem, these constraints, they have the stochastic right hand side. So the demand is stochastic, and these scenarios I enlisted them here. So we have three scenarios with each with some probability 0.3 or 0.4, and then for example, in the first scenario, the demand for the first product is 50, for the second is 20, and for the third is 200. And for in other scenarios, it works analogically. I will again turn off the webcam. Yes, and now we are asked to build such model. So our model will be almost exactly the same as deterministic model, but we need somehow to choose this right-hand side parameters in such a way that whatever scenario realizes in the future, these constraints are never violated. And let's look more closer on the product 1, for example, the constraint of product 1. So what we basically need to do according to the fat solution, we will need to choose, okay, what we will put here as the right-hand side, 50, 150, or 250. That's what we need to decide. What will happen if I choose to put here 50? So if I choose this constraint that the production should be less than 50, which is the right-hand side and the constraint for scenario 1, let's imagine that then in reality scenario 2 realizes. But still my y 1 will be at most 50. If it's at most 50, it's still smaller than 150. So this constraint will not be violated for scenario 2. Now let's look at scenario 3 again. The same logic. If scenario 3 realizes in the future, its constraint, which will be y1 less than 250, also will not be violated. So it seems that I chose this parameter correct. Now let's assume what will happen if I would choose the value of this parameter 250. So we choose that y1 should be less or equal to 250. We optimize this model, and let's say that we will have here the production should be 250, our solution. But then in the future, scenario S1 realizes, and according to this scenario, the demand for the first product is 50. And therefore, when we made the decision that the production should be 250, but according to the scenario 1, it should be less than 150, we will have the violation of the constraint. So we cannot choose this parameter to be in the fed solution. In the same way, if I choose a parameter of demand for the product 1 from the scenario S2, I will also not be able to satisfy the constraints for any of the scenarios, because if scenario S1 again realizes, it might be that my planned production will be more than 50. So the only option that I have, it's 200, it's 50. The same logic is about demand, which we choose for product 2 and for product 3. So for product 2, we choose again the smallest demand among all the scenarios. And it's 20, also from scenario 1. And then it's 200 for the product 3. And if I choose these parameters, which all happen to be from scenario 1, our decision, it will not violate any of the scenarios, whatever of the scenarios realizes in the future, any of their constraints. And if I go back to the lecture, here you have again the same explanation. And so as this right-hand side, for less or equal constraint, as it's here, you choose the smallest parameter value. So again, as a general rule, if you understand how this logic works, so we have here less or equal constraint. Therefore, we need to choose for the fed solution the smallest possible right-hand side among all the scenarios. If you will choose not the smallest one, then it might happen that your decision will violate the smallest one. So as I told before, if I would choose here 150, it might happen that my decision will violate this constraint 50. Of course, if we would have the constraint of another direction, let's imagine that we would have the constraint y1 should be more than demand y1, right? And for demand 1, we again have the same parameters. So if I would choose 50, as I did it for the less or equal constraint, this y1, of course, it would be according to our solution for this fat solution problem, it would be at most 50. And the solution at most 50 or 50, it would violate the constraint for the scenario 3. So if scenario 3 would realize this y1, it would be supposed, so now it's 50. But if scenario 3 is realizes, it would have to be larger than 250. And 50 is, of course, not more than 250. Therefore, for the fat solution, when for the constraints with more or equal direction for inequalities, we choose the highest parameter of the right hand side, which would be 250. And the same would be for product 2, it would be also 250, and for product 3 it would be 500. So this was the fat solution when we choose such right hand side in the constraints that whatever scenario realizes, not of the constraints are violated, or 100% of constraints are not violated, are fulfilled. Why it's called fat solution? Because our aim here is somehow too much, so we want not to violate any of the constraints. And also in the lecture you see that it said that such approach, it's very pessimistic, or it's very expensive, because we assume, so to say, all the cases that we might have, and also the worst case, or yes, with the smallest probability, with small probabilities. And therefore, if we want to take into account all the scenarios, normally it's really negatively influences our objective function. In the next two sub exercises, bullet points, we want to create models that guarantee that model is feasible in 60% of the cases. In other words, we want to build a model that guarantees that the constraints of the scenarios with the total probability of 60% are guaranteed to be feasible. So, and first approach, there are two ways to do it: so-called quantile approach, based approach, and approach with binary variables. In quantile-based approach, we again need to choose the right-hand side by ourselves. So this 60% here, it's also called alpha. So I will write down that alpha is 60. Alpha is 60. And before, for fat solution, it was 100. So fat solution is a special case of what we will look now, when probability is, or alpha is 100%. So let's have a look at the, again, first constraint. So if we choose as the right-hand side not 50, but 250. And yes, this is less or equal constraint, as it's, I mean, without these modifications and experimentations. As I said before, of course, 250 in guarantees that scenario, that constraints of the first constraint of the scenario S3, it will not be violated. But it doesn't guarantee that constraints of scenario 2 and 1 will not be violated, because y1 according to this right hand side can be still, let's say, 250 and 200, and of course 200, it's not smaller than 150, right? So such right hand side, it guarantees only that scenario 3 will not be violated. Scenario 3 has this probability 30%. It means that when we choose right hand side for the demand constraint of the first product as the data value or parameter from scenario 3, we guarantee the alpha level of 30%, but we want it to be 60. Now let's go to the next scenario, scenario 2. If we take the parameter 150, then with this right-hand side 150, we will of course guarantee scenario 2, so it's 40%. But of course, if this y1 will be smaller than 150, of course it will be then automatically smaller than 250. So here we will guarantee the feasibility for 30% of the cases plus 40% of the cases, which is 70 in total. And since we have here discrete scenarios, it means that in some cases, like in this case, we will never be able to choose some right-hand side that guarantees definitely exactly 60%. It should be, we should choose this parameter until the time that at least 70% of the cases are guaranteed. So we choose this right-hand side on the level 150. And we don't need to check the scenario 1, because if we take from scenario 1 the parameter, it will be 100% of the cases. Now, of course, so all three parameters for every of the constraints, they develop or change in the same direction for every scenario, or they are ranked in the same way. So for the first product, demand in scenario 1 is the smallest, and in scenario 3 is the highest. For the second product, it's also the smallest for the first scenario, the highest for the third scenario, and for the third product itself. That's why this approach, it will be the same for every product, for the demand of every product, and it means that for every product we choose the demand as the right-hand side of scenario 2. So here it will be 110, and here it would be 125. Then if we would choose, for example, some people maybe they don't really understand this concept, they say, why don't we choose scenario S1 and S2? The thing is that when you cannot, so to say, choose S1 without also including S2 and S3, because so if you think about these constraints and these values, if we choose S1, we automatically satisfy S2 and S3. So we cover all the cases because we have this relation between the scenarios. For the more or equal constraint, the situation would be opposite. So actually, for more or equal constraint, since S2 is in the middle, we would also choose S2, but the logic would be the opposite, the same in the same way as it was in the fed solution. Now, if we would have something like this, that we have three scenarios, but it's not always that scenario S1 is for all the product, the demand is lower than S2, and for S2 is lower than S3. Let's say that we would have here uh, 110 and here 20. So you see that for the second product, this relation, it doesn't work like that. Then we wouldn't be able to use this approach for this case. And actually, it's only the coincidence that we can use this approach for three constraints, only because this relationship, it's like that for all the products, for the demand of all the products. And in the lecture, you have it's noted. There's this quantile-based approach. So it can be used only for uncertainty in right-hand side. That's what we have here. And also it's mentioned somewhere that it can be applied only to one single constraint. But here we had an exception because again, this relation among for every product among the scenarios for demand, it's always the same. Of course, if we would like to achieve the level of alpha would be not 60 but 70, so here 70, it would still work because our factual achievement or feasibility level, feasibility probability, it's 70. If alpha would be 80, of course, 70% wouldn't be enough, and we would have to change our decision, and our decision would be then to use the right-hand side and take this data from scenario 1, which would be the same as fed solution, and it would again guarantee the feasibility in 100% of the cases. Now, this was the quantile approach. In this approach, we calculate the right-hand side, so to say, by ourselves. But the next approach is a binary approach, binary variables approach. It's bullet point C. The idea of it that we we want the model itself to define this right-hand side values. And this approach, it consists, so to implement it, we need to add some objects to our current model. So if I go to the lecture, first what we want to add, the approach with binary variables, we want to add this constraint, which is the sum for every scenario of the probability of the scenario multiplied by variable ys. Ys is the variable that says, or that defines, or yes, that shows our decision whether the constraints of scenario S are taken into account. So for example, in the example here, the example, we see that 0.1, which is the probability of scenario 1, is multiplied by y1. And then if y1 is 1, so if we take into account the constraints of scenario 1, 0.1 multiplied by 1, it's also 0.1. And then we calculate the same element for every scenario. And the sum of all active probabilities should be, in this example, 0.7, but in our current example, it's 0.6. It's this alpha level. This is the first element that we need to add to the problem. For our problem, it will look as this constraint will look as 0.3 multiplied by y1 plus 0.4 multiplied by y2 and 0.3 multiplied by y3 should be more or equal to 0.6, right? Then, for example, if we activate constraints of scenario 2 and 3 and y1 is 0, the total sum will be 0.7, which doesn't violate this constraint. This was the first element, and now we need to add several constraints for demand. So we need to add constraints for this part. We will modify these constraints, and we can do it in basically, there are 3 ways to do it, 3 formulations. So you see here in the lecture, there are 3 different possible formulations. You have here the examples. So the first approach, I will now implement the similar idea for our problem. So let's look at the demand of product 1. It should be less or equal than something. And then how do we formulate the right-hand side using these binary variables and maybe something else? The formula how we formulate right-hand side, it's here. So BS, it's the right-hand side of the so it's the largest parameter value of all the possible parameter values among all the scenarios. So you see here in the example is 1500, and in our case it is 250. Then according to this formula, then we have minus, and then here we put the difference between this largest scenario, or scenario with this largest parameter, 250, and the next second largest scenario, and this difference it's 100. So here we put 250 minus 150, it's equal 100. I will write it as it is without details. So it's 100, and we multiplied by the decision variable y and then s minus 1, so that second largest scenario. So it's y2 in our case, and then minus, and again now the difference between this parameter for scenario 2, 150, and scenario 1, the smallest scenario, so we came to the end, it's 50, and it's again 100, so minus 100, and then y with the index 1, because that's the index of this scenario for which we calculated. Now, how this all works? Let's say that we decide, or let's model some decisions. So let's assume that as for the fat solution, we decide that we include, we take the right hand side of S1, and of course we automatically then will include S2 and S3. So the decision variables, all three decision variables y, they will be 1. It means that in this right hand side calculation, y1 will have value 1, sorry, y2, and y1 will have also value 1. And then if we now calculate this right hand side, it will be exactly 50. So it will be exactly the right hand side of this scenario with this parameter from the scenario S1. Now, if I go back to the solution which we made for alpha 60, which we, so to say, made by ourselves, but now we want the computer automatically do it. According to that decision, we didn't include scenario, the most restricting scenario S1. We allowed it to be violated, but we included S2 and S3. So it means in this right hand side, y2 will be 1, and 250 minus 100, it will be exactly this number. And that's exactly our decision which we made. And then if we also put these values of decision variable y to this constraint, let's check. y1 we don't care about it, we don't include it. y2 we included, and y3 we included. So again, it will be 70%, which is more than 60. So it's using these decision variables, we, so to say, automate what the calculations that we did before. And now, this was for product 1. For product 2, the logic is exactly the same. So I will just write down, so it's 250 minus 140 y2 and minus 90 y1, and then y3 difference 275 y2 and minus 25 y1. So these are constraints for all demand, for all the products, for all the constraints that have stochastic elements. And now let's check what else do we need to add here. So the formulations that we have so far, nothing doesn't prohibit the computer to do something like that. Set y1 to 1, y3 to 1, and y2 to 0. But we know that it's not possible. We know that due to the values of the parameters, if we activate scenario 1, it means that scenario 2 is also automatically activated. So it can be only like that. And it means that we can say S3, it should be always larger, or y3, so the decision variables for scenario 3 should be always larger than y2, and y2 larger than y1. And in this case, situation like this, it will violate such constraint. So we need to write down now this constraint as y3 more than y2 and y2 more than y1. And actually, yeah, basically, and y3 should be always 1. And this is exactly the same constraint we have here. So this was the first approach. And now the next approach, it's the same thing, but reformulated. So here, instead of starting with the largest parameter, or yes, we see here, since it's less or equal constraint, we start here with the largest parameter value. We start with the smallest one, and then we add up the values multiplied by the 1 minus decision variable for the scenario. And this works almost exactly the same. So I will not now reformulate this again for this case, because the logic is the same. Instead of taking out the difference, we add up the difference. So this was the second approach. And then the third approach, or formulation 2, it's using the big M notation. And what this big M is doing. So let's take a look at the constraint. For example, so this will be big M. And this will be the, again, formulation of the demands constraints. So this was the formulation with binary variables 1, and this will be with binary variables formulation 2 with big M. So what's the idea here? Let's formulate the constraint for product 1. So 3 constraints for all 3 scenarios. So y1 less than 50, y1 less than 150, and y1 less than 250. Oh, actually, I just saw that we have some problems with the decision variables, because we call here the decision variables for production amount as y, and we call these binary variables also as y. Even so, these are different variables, so we need to use some other notation to avoid problems. Let's use for them instead of y, z. So here everywhere, instead of y, it should be z. Because otherwise it might be confusing. So here it's everywhere is z. And here, of course, as well. Now, when we go back to the constraints, so these are constraints for product 1 for 3 scenarios. And now the logic which we want to apply now is that, so when this Z1, when Z1 is activated, so if Z1 is equals to 1, this constraint should be active, because that's the meaning of decision variable Z1. When Z1 is equal, somehow this constraint, it should be turned off. I don't want to care about this constraint, because Z1 equals to 0 means that I don't take into account constraints for scenario 1. Now the question is, how can I somehow dynamically modify this constraint that it behaves in such way that it's activated and deactivated? Let's first look how can we deactivate, so to say, any constraint. You see that here y1 is less than 50, so it's quite restricted. But what will happen if I add to the right-hand side some very huge number? And we before had some huge number, which is m. So m is some very, very huge number of almost infinity. Now if I say that y1 is less than 50 plus something almost equal to infinity, it means that basically, even so this constraint exists, y1 it's not anyhow restricted. So my production is not restricted by this constraint. Maybe restricted by other constraints, but definitely not by this. So it means that I want this m to be here when z1 is equal to 0, right? Because z1 equal to 0 means deactivated, and m is really what is deactivated. And I want this m disappear when z1 is 1. So what should I do here? I should just multiply m by 1 minus y1. Z1, sorry. Oh, it's not really good, this Z1. And now if Z1 is equal to 1, 1 minus 1 is 0, m multiplied by 0 is also 0, and it means that this constraint is activated. When Z1 is equal to 0, you can make the calculation and you will see that the m will still be there. So I will have this constraint deactivated, and that's exactly what I want. And I do exactly the same thing for all the constraints. So it should be y2. No, it should be. So it's for the first product. For the constraints of first product for all the scenarios. So here I take the right hand side of scenario 2 and I write down 1 minus z2, and here m 1 minus z3. When I did it for product 1, I would need to do exactly the same for demand scenarios for product 2. So it would be y2 less than y2. And then for also y3. So it's quite lots of constraints. It was 2110, 250, 200, 225, 500. And of course, this m everywhere. And then 1 minus z1, 1 minus z2, 1 minus z3. And here again, 1 minus z1, 1 minus z2. All right, these are quite a lot of demand constraints. And this is related to product 1, product 2, and product 3. So, and that's it. So I will ask to do something in additional for this sub point. Yes, so we are also asked to formulate it using the using the MPL software. But now let's look like, so our formulation using the binary variables, the type 1 formulation, it will include all the constraints of the deterministic model except the demand constraints. And instead of the demand constraints, we will have all these constraints, where one constraint guarantees that we achieve the reliability level 60%. Then we have one demand constraint for every product. And then we have this relation between z variables. And we had to use here another notation for variables, which were in the lecture y variables, because we have already y variables in the model. And the formulation 2, using big notation, it will include the deterministic model, except the constraint with stochastic parameters, which are demand constraints. It will also include this constraint which guarantees the level, reliability level. And then it will, the demand constraints will look like that, quite lots of constraints with big M. We have here constraints for every product and for every scenario. We are asked to formulate it in MPL. I will not write now it from scratch. I will open, let's have a look at the solution files that we have. So the formulation F1, so formulation 1. Again, it's the same deterministic model, and the change here, it's first of all this demand deltas, which we calculate. So the demand deltas, they correspond to this 100 and 100, 140 and 90. That's one parameter that we calculate manually. And then, of course, the constraints. Decision objective function, we change nothing here. And so the demand for every product, it's calculated in the same way for formulation 1 as we did it now. We left-hand side is the same, that's the production of the product, and right-hand side, so it should be less than demand for this product in scenario 2, in 3, sorry, minus the demand delta, so the difference between demands of scenario 3 and 2, and minus the difference of demand of scenario 2 and 1. And then we have this constraint with for reliability level, and then the constraints for y, which in our formulation we named as z. And the next solution is with big M notation. The next model. And here we have even less differences. So we basically, in the constraints, we put on the right-hand side demand, the same what we did here. So the demand of the scenario plus some big number, which we choose here as 10,000, it suffices, multiplied by 1 minus 1. And it's, so you can see that here we have only one line in the modeling language to represent all these multiple constraints. And then we have, again, the constraint for the reliability level. And now, up to now, we looked at the case when stochastic parameters, as in the Dakota model, are only at the right-hand side. And for the formulation 2 with big M, we see here it says that in contrast to formulation 1 and quantile-based approach, it's also possible using this formulation to define the chance constraints, which have the technological coefficients, so the left-hand side coefficients, also stochastic. And to analyze this situation, we are provided here the bullet point D, which is the extension to the previous Dakota model. And it says that in addition to the demand, to the stochastic demand, it has 3 scenarios. We have also 3 additional scenarios for the consumption of the lumber. So lumber is the first material, and now we assume that differently as before, this consumption, it can also differ from scenario to scenario. And for that, we have also 3 scenarios with probabilities 30, 40, and 30. And it's mentioned here that the demand and scenarios and consumption scenarios, they are independent. It basically means that if we have scenario 1 for the demand, it doesn't mean that for the scenario 1 of demand, we always have the scenario 1 for consumption. We can have any scenario for the consumption. Let's look what can we reformulate, or what should we formulate in the deterministic model, and as a basis, since in addition to the stochastic demand, we have now also the consumption of lumber. As a basis, we will use this model with a big M. So again, this model, it consists of the objective function, material constraints, non-negativity constraints. It also has this constraint for reliability level, and of course the M constraints themselves for the demand. Before we dive into the formulation of constraints, let's think about the scenarios. So before we have 3 scenarios, now we have 3 demand scenarios and 3 scenarios for this lumber parameter. They are independent. It means that we have the first scenario, S1. In this first scenario, we have the demand from scenario 1. So it's demand 50, 20, 100. And we have the consumption of the lumber. I don't remember which letter we used. Let's say that it's L. Also from the first scenario of the lumber consumption. So it's 5, 4, and 1. Then we have next scenario, scenario 2, where we have the also demand from scenario 1, but now the consumption of lumber from the lumber scenario 2. Then we have scenario 2, again demand 1 and lumber consumption 3. Then scenario 4, it's the demand 2, lumber consumption 1. Scenario 5, again it's demand from scenario 2, but lumber also consumption from scenario 2. So we have all the possible combinations of them, because for demand 1 scenario, we have 3 possible lumber scenarios, and all their combinations will provide us the number of scenarios, which will be, of course, 9. Now, what's the probability of every of this scenario? The probability of D1, the scenario 1 of the demand, it's 0.3. And the probability of lumber 1, if I go back here, so of the first scenario of the lumber, it's also 30%. So it's 0.3. And their total probability, it's 0.3 by 0.3, which is, so it's 0.3 by 0.3, which is equal to 0.09. Now, the next combination, it's D1, which has probability 0.3, and L2, it's 0.4. So 0.4 3 multiplied by 0.4, it's like a conditional probability, is equal to 0.12. And so on. That's how we calculate the probability of every of our new scenarios. So it means that now, using these binary variables, we need to formulate the constraints for every product and for every demand of every scenario. And then again, with these binary variables, we need to reformulate this material constraint because this is the constraint for lumber. And these coefficients, 8, 6, 1, they change from scenario to scenario. Now, how will look like the constraint for product 1 in this first generated scenario, S1. Of course, it will still have the demand from the first demand scenario, so it will be 50. Then, how will it look in the second demand, second scenario? Demand there will be the same, so I can write down it here as y1 less or equal again to 50, but now I have here another decision variable naturally for scenario 2, so it's 1 minus z2. Then for the scenario 3, according to our new scenarios, demand would be again the same, it's 50, right? But then we come for the product 1 to the scenario 4, and we see that for the scenario 4, demand is changing. And for the scenario 4, we have the demand from the demand scenario 2. And this demand for the first product for demand scenario 2, it's 150. So what should I change here? I just write down that the production of product 1 less or equal than 150 plus m 1 minus z4, because this is the first scenario, the fourth scenario. And I would continue in the same way until the 9th scenario. Now, after I formulated these constraints, I would then create constraints for the product 2. And this would be for the scenario 1, for the product 2, it would be 20. So it would be 20 plus m 1 minus z1. So here we start product 2. And then in the same way, I would create these scenarios, demand scenarios for product 2, and then for product 3, and I would be done with the demand scenarios. But we also have the finally the lumber production constraints, which should be also adapted. So in scenario 1, we have the lumber production from lumber scenario 1. So these coefficients in scenario 1 of lumber are 5, 4, 1. So I would write down here 5, 4, 1. These are coefficients, and as the decision variables, I take y1, y1, y2, y3, should be less or equal to the available amount. Available amount doesn't change according to scenarios. It's still x1. So x1, and then again plus m1 minus z1. Then this scenario, this constraint for the scenario 2. In the scenario 2, we have the demand from the first demand scenario, but lumber amounts from the second lumber scenario. So it's 772. I just rewrite this constraint with the coefficients 7, 7, 2, y1 plus y2, and 2, y3, less or equal to x. Here should be 1. x1 plus m 1 minus z2. And I would continue like that for all the scenarios where lumber it's one from the lumber scenarios 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. Now, so this would be the demand scenarios, the demand constraints, and the lumber material constraints in this new model formulation for the case when left-hand side coefficients are also stochastic. Then I wouldn't, of course, need this constraint. I would include these constraints because they are not stochastic, they are not changing. Then this constraint, which guarantees the alpha level, of course, it would be, I need to modify it. I need now to write it down as 0.09 multiplied by Z1 plus 0.12 multiplied by Z2, and so on, more than 0.6. Yes, and this would be the modified problem. It's quite lots of writing in this form. And now let's check how it looks in the MPL, because we are asked to formulate it in MPL. In MPL, it looks much more compact and much more easier to understand. So this is the MPL formulation. What has changed here? So we see that consumption L, it's the new data vector. Actually, it's multidimensional vector. It's consumption of the lumber. Now it has two indexes for products and for every scenario. So product, it's this are rows, and scenario index, these are columns. And we see that if you imagine these columns, for example, first column, it's related to scenario 1. In the scenario 1, we have this coefficients of lumber consumption for three products at 4, 5, 1. And it's exactly what we had here. It's 5, 4, 1. Then here we have consumption of lumber for the second lumber scenario, then for the third. And then it repeats again. And in total, we have 9 columns, which are 9 scenarios. The demand, it's almost the same as it was in the previous stochastic version, but it repeats now every 3 scenarios, because in the first 3 scenarios, it has the values from the demand scenario 1. And this corresponds here. So it was for the product 1. We had in the scenario 1, Z1, Z2, we had there the demand for product 1 from the demand scenario 1. Now we have the probabilities, and probabilities we calculate manually for all the 3 scenarios in the way exactly one that is shown here. Like we multiply its conditional probability, so you multiply probability of the demand scenario with the probability of the lumber scenario. And now you see it looks much more compact than in mathematical expanded formulation. So here we have the lumber constraint. So in the objective function, we don't change anything. And what we change is the constraint for the lumber. And here we add this big M, the same logic as before. And the demand constraint, it's the same as was in the previous formulation. Yes, and alpha level, we also don't change these constraints, because if we change the data, automatically this constraint would be changed. Now, if this this is the case when these two scenarios of lumber consumption and of the demand, they are independent. What if they were dependent? If we could say that always when we have scenario 1 for demand, we have scenario 1 for lumber. And when we have scenario 2 of demand, we have scenario 2 of lumber. Then we wouldn't need to check all these combinations. We would have something like this. When we have D1, we have L1. When we have D2, we have L2. And when we have D3, we have L3. So we don't have 9 scenarios, all the possible combinations. We have, as before, 3 scenarios with the probabilities 0.3, 0.4, 0.3. And in the solution, there is also MPL formulation for this case. So we wouldn't also need this. And this case we would call when these two stochastic parameters, they are dependent and they don't generate all these possible constraints. So, what is important is that only using this M formulation for chance constraints, binary formulation version, we can have stochastic parameters in the left-hand side. If we would use quantile approach, or if we would use the previous binary formulation, we wouldn't be able to model this case. So this were all the tasks related to chance constraints. And in this task, we look at the fat solution when we require that all the scenarios are constraints for all the scenarios are feasible. And this is the most expensive solution, because then we look at the worst case. In our case, at the scenario with lowest demand. Then we tried this quantile-based approach for reliability level 60, when we calculate by ourselves the right-hand side parameters, and we take the parameters from that scenario that guarantees the cumulative probability of 60% of the constraint being feasible. Then we tried the option with binary variables, and there are let's say 3 formulations with binary variables. First two, they don't use big M, and they allow only stochastic parameters being in the right-hand side, and formulation with big M, it allows for the stochastic parameters being also in the left-hand side, which we looked here. And we had here's the case when two stochastic parameters, consumption and demand, are independent, which means that they generate all the possible combinations between the scenario for consumption and scenario for demand. So they define 9 scenarios. There are 9 combinations there for 9 scenarios in the final model. In exercise 2, we are asked to look at the robust optimization, or yes, have some intuitive understanding of the robust optimization. In the lecture, you have lots of details. What is the idea of robust optimization? The idea, as it's written here, that some parameters, they fluctuate in some margin, in some margins. So, for example, here you are asked about the robust optimization for the case when demand is fluctuating in the margin plus minus 2%. So in the previous examples related to discrete scenarios, we assumed that demand it can have some values with some probabilities, which we call the scenarios in the future. Here we assume that it's fluctuate plus minus 2%. It means that, for example, in the deterministic model, the demand for the product 1 is 160, but now we are told that it can fluctuate in the margin plus minus 2%. So we have 160. It's something like mean value, but it can be minus 2% and plus 2%. So it fluctuates from 0.60 from 160 multiplied by 0.98. Yes, 1568. 1568 or 1632. So it can be any value on this in this range. It can happen because of the measurements, because of probability in the real world, and so on. And the same is happening for the demand for product 2 and for the demand for the product 3. And what's the idea basically? The thing is that if we now take this demand, its mean value, so 160, 115, and 290, and then if we realize that its real value is 156,8, it means that our decision might be infeasible. Because if we take this right-hand side as 160, so mean value, or even the highest value 163, and if we see that the real value was 1568 and our decision is 160, then it will be infeasible. So the idea of robust optimization is to look at every parameter and every fluctuations of the parameter and take that parameter values that guarantee that this constraint and that all constraints, they will be feasible. So we look at something like a worst case. It's quite similar to the FAT solution. And this updated problem, so when we change the problem from deterministic equivalent to one which guarantees our problem is always feasible, taking into account the possible fluctuations in the parameter values, it's called the robust counterpart. So we are asked here to formulate the robust counterpart. And the only thing that we need to do, we just need to substitute this all mean demands with the lowest possible value of this demand. So it will be 1568. Then here it will be 115 multiplied by 0.98. And here also will be 290 multiplied by 0.98. And this will be The same model, but with these demands, will be the robust um, counterpart with guarantees that even if fluctuations work against us, with the problem will still be feasible. And then you have many techniques how to really define these parameters, because in this case it's quite simple. You just look at every constraint and check takes the smallest value of the parameter. But if you have very big problem, then to understand which value of the parameter is really um, guarantees feasibility, it's often not so easy, and then you have a special technique that um, provide you these parameter values. So this was shortly the second exercise about the robust optimization, and this is it for the today's tutorial. We'll have only one more tutorial and exercise sheet number 6. So we look today at the chance constraint programming and shortly at the robust optimization. So have a nice week and thank you for your attention.